going to look at how to find the area between two curves. And we're going to do it with this particular example where we have the red curve, y plus 4 over 3 is equal to the square root of x plus 2, and the blue linear function y equals x minus 2. So we can see that enclosed area here in purple. And we can think of that purple as being made up of lots and lots and lots of tiny little rectangles, which we could choose to draw, say, parallel to the y-axis. You get the idea. I don't need to draw all of them. And then to find the area between the curves, we just need to sum up the areas of all those tiny little purple rectangles. And each of these infinitely thin little purple rectangles will have a width in that direction parallel to the x-axis of dx. And the height will be whatever the y-coordinate here is on the red curve minus whatever the y-coordinate is here on the blue curve. So each rectangle's height is y red minus y blue. And then the lower limit of integration will be whatever the x-coordinate of the left endpoint is. And the upper limit of integration will be whatever the x-coordinate of the right endpoint is. So now it's just a matter of using the given information to fill in all the pieces. And to find y red, we just need to rearrange this a little bit. Multiplying both sides by 3, we get y equals 3 root x plus 2. And then we need to subtract 4, put that over here. And y blue is easy, that's just x minus 2. And to find those left and right endpoints, we just need to find the coordinates of these intersection points, which often we're doing these problems with a calculator, and then we could use the intersect feature on our calculator to discover the x-coordinates there. We'll do one example here of working that out by hand, just so you can see how it works. So that's just solving this simultaneous system of equations. We want to know where 3 root x plus 2 minus 4 is equal to x minus 2. Add the 4 to both sides, square both sides, we've got a quadratic, so bring everything to one side. And that factors nicely. So we get, as we might have guessed, x can be 7 at the right endpoint and x can be negative 2 at the left endpoint. So now we can fill in negative 2 for x left in our limit of integration and 7 for x right. Now all that's left is to evaluate this integral, and this one can be done by hand, but it's pretty tedious. And normally when this tedious, you'd have your calculator to do, so let's just do it that way. All right, so we do math and 9, and we want to go from negative 2 to 7. And I have in the y1, I have put the red function, so we'll do alpha trace and get y1, and alpha trace y2, dx, enter. That's an interesting calculator result. If you do this by hand, you'll find out that the answer is actually exactly 13.5. So we have solved the problem. I do, however, want to look at another way we could have done this. When we drew the rectangles initially, we decided to draw them parallel to the y-axis. We could have chosen to draw our rectangles parallel to the x-axis, like so. And we could have just as easily built up the enclosed area this way. What would the integral look like in this case? Well, each of our little rectangles would now have a height of dy. And the width would be this bigger x-coordinate, the x-coordinate of the blue, minus this smaller x-coordinate, the x-coordinate of the red. And our lower limit of integration would have been this y value at the bottom intersection point while the upper limit of integration would have been the y value up here. And x blue would be what we get by solving that equation for x. So that would be y plus 2. While x red would be what we get by solving this equation for x. That'll come from squaring both sides, so we get y plus 4 over 3 quantity squared minus the 2 will equal x. So that's our x red. Now we have to subtract off that whole expression, so we need another set of parentheses in here. And finding the limits of integration is a little bit easier in this case because we already have the x coordinates and we know that y is just 2 less than x. So this point has coordinates 7, 5, making the upper limit of integration here, y equals 5. And this point has coordinates -2, -4. So the lower limit of integration is -4 because that y bottom is -4. Okay, let's take a look at the calculator and work this out. We're going from -4 up to 5. And we got to be careful with all our parentheses here. So we'll use alpha to get a y. And if I want to get fractions, I can do alpha y equals, and there's a fraction button there. I think I need one more parenthesis. And then dy. And we get 13.5, which is what we were hoping for, because we know the area shouldn't depend on the way we calculate it.